So let's talk about LED lights for a second and make a comparison between them and the old kind of bulb, incandescent bulb. Come on, get into focus. All right, so we've got the old bulbs, incandescents, and then we have the new bulbs. Not even a bulb, it's LED. So I'm going to draw this real big. Let's see how this would look. And the old kind of bulb, incandescent, has a filament inside of it. And a filament is not a very efficient resistor, right? And that's the point of it, is that as electricity comes from your plug, got the two prongs there, right? And then the ground at the bottom. That's terrible. You know, these things, right? We've got electricity comes out of one prong, up the plug, into one of the two terminals on the light bulb. And from there it goes up into the filament. The filament is having a hard time letting the electricity go through. And so all the friction generated by the resistance turns into so much heat that it starts to light up, making the light bulb work. And whatever is not getting used keeps going to complete the circuit, comes out of the other part of your light bulb into the second wire that makes up, when you have inside your plugs, there's actually two different wires running inside there. The second wire, and goes back into the home, into the other plug. And the difference between what's coming in and what's going back out, that's what the meter reads at your house for all of the electricity being used. This is, like I said, 110 volts approximately. And remember, this is not DC, but it's coming out of the house. It's alternating current. Subsequently, if you were to try to grab onto alternating current, you wouldn't be able to hold on to it. You'd be able to let go and get off of it. You wouldn't get stuck to the current because it's alternating, literally, because the wave goes up and down. And you can't stay on it. But if you were to touch a live line in your house, right, you would feel it. But it's not enough to kill you. But it's enough to let you know that it's hot or on. In any event, these light bulbs are very inefficient. 90% of the electricity, or 90% of the energy being generated by the electricity is lost in the form of heat. And maybe only 10% of that electricity is really contributing to the light. Plus, as a technology, even though it gives us the benefit of not having to use candles, one of the outcomes or the trade-offs is that this thing still gets super hot, it's inefficient, and they burn out often and have to be replaced, all kinds of other trade-offs. But it was neat how Edison's crew figured out a way to plan the obsolescence of a light bulb, where they could time it for how long, how many hours it would take before this filament burns out, and you would need to replace it with a new one. If they used a different filament, there are patents for light bulbs that last. Some have still lasted since that time, 100 years, they're still running. I'm sure it would be much more expensive for that, whatever the filament is made out of, as opposed to the alloy made out of tungsten steel and some other tin or whatever else makes up the alloy now. So we take a look at the LED. This is supposed to be an improvement or better technology because these only lose 10% of their energy to warmth, and these are 90% efficient, let's say. So you get a whole lot more efficiency. And inside of the LED, there are two pieces of metal. You can look because one side will be different shape than the other, and that's one way you could tell which side of the LED is plus or which side is minus with the legs down here. Now with the battery, it doesn't matter plus versus minus. Or my battery. With the light bulb, it doesn't matter. If you're in 5th grade and you were hooking up your battery pack directly to your light bulb, it wouldn't matter if you touched the positive or negative sides, which way they went. It would still be fine. And then LED stands for light emitting diode. A diode. Now, a diode refers to an electrical component that only allows electricity to go in one direction, meaning that it has polarity. So we'll see in a little bit when we start to hook up the light pack to the battery pack to the LED, that the LED, the battery, will have to be facing a certain direction. Which side is touching becomes important, or else it won't light up. Keep that in the back of your mind for troubleshooting your circuits later. Now inside the LED, we have these two different metals that are semiconductors. It's a semiconductor. Semiconductor. And the semiconductors are metals that have these openings in them, or if you looked at them under a microscope. Apparently, I never have, but as electricity comes through, charge starts to build up on top of these holes, and then over here, the charge gets pulled, and electrons are arcing over. Arcing, an arc, when you see a bzzz, if you ever pull the vacuum out of the wall too fast, the plug while you're still vacuuming and the vacuum is on, and it's a real nice dry day, you might see the little spark come from the outlet to the plug, that arc. Right, so this is arcing here, and that's what's going to give us the light. And the way the light's going to really shine is, one way that helps us with how bright they are is if you look closely at the inside, you'll notice that this plastic has been shaped into a concave shape or an angle, so that as light comes out, it emits on this wide angle. And the type of LEDs that these are wide angle LEDs. Specifically, that's what they're called, wide angle. And when you're buying LEDs, you don't know just by looking at the LED when it's off what color it is going to be. The color that comes out will be based on the type of semiconductor material, right? One way to change the color of an LED, if it's a white LED, is you could always paint the LED or put marker around here or tissue paper. That would totally work, but you would be losing some of the brightness, the luminosity. We measure light in, one measurement of lights is in lumens. So just keep that in mind for future reference. All right. Now let's move on to our circuits, because we want to put together a simple circuit first, and then talk about it as a schematic diagram, and then we'll put together a parallel circuit. So why don't you get your circuit components back out. And whatever you're going to use as a wire cutter. As we are going to be putting together this circuit, even though your switch might look a little bit different. Let's take a look at a couple pictures of some things students have made in the past. I'll just run you through a bunch. In this design challenge, I give you some requirements that you have to meet with your solution to whatever problem you pick. That light can help be part of the solution. But everybody will have their own unique requirements that they add depending on the problem. But everyone also has to meet a couple basic requirements that I give to everybody, which is that you have um, at least 3 LEDs being utilized, that you have a way to turn your device on and off. This student here has a switch built into the glove. You're asked to balance form and function, meaning that things will look nice but also work well. So having a bunch of wires hanging out here might be a detractor in that situation. But hiding the battery pack, which I don't see the battery pack here, that's great. You want to hide the battery pack, but also make the battery pack accessible so you could change the batteries if need be. But things like having hot glue hanging all over the place, that would not be balancing your form and function. But for this student, he may have had his own requirements, like the lights needed to, be able to help illuminate things that he's working on with his hands, that the lights can't get in the way of when he's holding a tool. I'm sure he came up with his own requirements, just like you will, based on your unique situation. And if you can make those requirements measurable, write them and write them out in a way where they could be tested and measured later, that's even better. This is the circuit diagram for a simple circuit, meaning that it shows the main components here with little symbols. This is the symbol for battery. Our source. This is a symbol for an LED light. This little triangle with the line above it and the 2 arrows coming out. And this is the symbol for a switch, which looks like a little gate, like you'd have a gate coming out of a fence or something like that. And you can see how that symbol suggests something could touch to turn on and separate to turn off. That's literally all that's happening inside of your switch device, right? Is when you push the button or pull the knob or tip the flapper over, something will turn on and off. And the reason it's drawn in a square like this is because wires, if you just start drawing a bunch of wire out the way it looks on your table, it would look like a bunch of spaghetti. Right? So a schematic diagram is a way to lay things out. And you start with a square like this and put in the 3 main components and then add out from there. They can get much more complex. Here's the end of a soda can. It got polished and was used to illuminate some light. You can see in this video, there's a bunch of different projects. Let's see if we can get it to play. Nope. You see them here? In this video, or I'm not going to play the video, but you can see a bunch of red cups turn into a lamp. Hey, there's somebody you may know. Maybe she could tell us later in class what the problem was that she was solving with her light up headdress. There's a light that hangs up in the closet so that when you get ready in the morning, you don't have to turn the whole bedroom light on and wake everybody else in the room up. Just a little bit of light. So here's a signaling device that students could use to let the teacher know they're okay, slow down, I need help. All kinds of neat ideas in here. This is what it will look like when we twist wires up by hand today. If you happen to have a switch that doesn't have pre-wired leads coming off of it, you just see the bare ends of the switch here, the positive and negative. It doesn't matter which side you connect to, right? Because all the switch is doing when you push the button is internally a mechanism is opening and closing that completes and breaks the circuit connection. So you'd have to take the little bits of wire and thread them through here yourself And if you want to put a little barrier inside here, like a piece of paper, shove something in there so that these two pieces don't touch. No, it doesn't make a short circuit if they touch. It just circumvents the point of the switch. So the switch, like it's like it nullifies the switch. Like the switch wouldn't even exist if these two pieces were able to touch again. Of course, when we get to soldering, you could solder those connections if you wanted to. But right now, we're not concerned about any soldering. Just saying that this is how we twist these wires up, starting at the bottom and then working to the top when we do. It's pretty neat. It's foam core up on the top. You can see the switch here has been pushed all the way down through a hole. And there's threads on the bottom of your switch and a little nut you could use to sandwich it onto something from the other side. That's pretty neat. Here's a student that baked their own sculptures of these fungus, and it was a type of clay that is translucent, and when we put light up behind them, they lit up. There's our switch embedded in there, that piece of driftwood. Now you only have so much time to work on this, and some of these pictures, some of these students had a long period, a couple class periods to work on theirs. It's a constellation. In this one, these are used as a signaling device where students are maybe sending out Morse code to somebody else. See a little bit of Morse right there. But in this design challenge, students had to make it so their light could do both. It had to be able to signal Morse code to somebody at a great distance, but it also had to be able to be used as a reading light. That's for fishing down off the dock to illuminate what you're doing, or if you're pulling up the crab traps. This is interesting because this already existed on Pinterest. The student copied exactly this thing that they found, and um, in that case, they really weren't designing their own thing. But that's okay. If there's something out there that you're going to utilize that's already designed, you just want to be able to do something different with it, innovate some feature or some component in some way, so that you can have your own spin on it, so to speak, which makes it your own project. That way you're actually designing something, not just recreating it from existing plans. This was a bug catcher that would catch bugs without the use of any chemicals. The light would attract bugs inside, and then there was all types of fly paper or double-sided sticky paper inside. All right, there's just some pictures. So let's put these away. Get back here to our circuits. All right, so we're going to take our AA battery pack. We're going to put 2 batteries in there. And when you do, I would like you to make sure that the red and black wires are not able to touch each other on either side, because we would then be short-circuiting. Right, what might also be a good idea before we do this is to pull some of this coating off. Now, if you do have wire strippers and you use these and you just give it a quick jam, it might actually cut the wire off too and be too powerful. All right, but I'm just going to pull a little bit, expose that wire. Do the same thing on the other one. Make sure they're twisted up real good on the ends so they're not frayed. All right, now let's take a battery pack and some batteries. You can see which way they go here. There's a little diagram. Tells you, but I always know the flat side goes up against the spring. And the reason the springs are there is to keep these things under tension so that the connection doesn't cease or break, right? And students have asked me before, what if I wanted to light up the inside of a wine bottle and I can't drill a hole into the wine bottle and this won't fit into the top? Well, then you could conceivably make up your own device that would allow your batteries to connect to each other in series, end to end. This does the same thing. It's one end pulls over to the other with that little metal connection, and make a device that holds your batteries together this way. Maybe even pull the springs out of a battery holder and pop springs in on each side and wrap the thing up in duct tape or something that would let you keep them pushed together tight, and then connect one end to here and one end to there. All right, so I'm not going to let these touch or I'd have a short circuit, but I'm going to take an LED that I've stripped the wires off of. One-handed. Same thing over here. Again, I want to strip off a whole inch or almost a whole inch because I need that extra wire to twist up. If I was soldering, I wouldn't need to expose much wire at all, just the littlest bit to connect to with solder. But we've got an LED. Now I said that these have to have polarity, or they have polarity because it's an LED, and the D is for diode. So if I touch them, well, there we go, we light up pretty good there. I got it right the first time. This works. Now if I were to switch the polarity, if I were to take the LED and flip it over, what will not happen is it will not light up. All right, it doesn't light up. So let's turn it back over this way. Now I know which way I got to light it. Cool. Now just to show you, I could have had you do this by yourself and ask you to figure out the answer by trial and error, doing a little experiment. But I'm taking another LED here, and let's see which direction this one has to go to light up. Just like that. Just like this. Okay. So if I were to put these two together now, I'm not going to twist them up all the way because I'm going to take it back apart. If I were to twist these two up, right, and get that little piece of wire off there. Now these two are connected just like they were when they came on the one big string, right? And these are now in series with one another. And if I try to light up the two LEDs, it won't work. Well, maybe it's the polarity. Let's check. It still doesn't work. Okay, the reason it doesn't work is there's not enough electricity, enough voltage to make it through the first LED and enough to continue to go through and light up the second one because of voltage drop. Voltage drop. All right, there's only 3 volts here, and I'm going to lose 1 or 2 of them by going through the first light, and it will not be enough to light up the second bulb. So that's why a series circuit, this would be a series circuit, will not work for us. That's why we're cutting these up. We need a parallel circuit. So I'm going to draw a parallel circuit as a schematic diagram so you can just have a quick visual of what that looks like on a piece of paper. Let's see, schematic diagram. So we want to have, this would be if we did them in series. So we've got the power, right? And then I'm going to use the bulb symbol for the sake of, just for the sake of time, instead of the LED symbol. There's a bulb. Then we would be going into another bulb. This would be in series, right? And then into another bulb. And we don't have a switch hooked up, but just by me touching and breaking the wire like that, that's the same thing as switching. So let's put a switch in. We'll say we've got 3 volts here. All right, so this is a series circuit. S-E-R-I-E-S. And series is bad because if one of these LEDs goes out, right, what happens? Electricity has nowhere to travel to get back to the battery and complete the circuit. So it's bad for that reason. It's also bad for us because 3 volts is not enough to light up more than one LED consecutively because of voltage drop. So we need a parallel circuit. So parallel circuit are 3 bulbs. We'll run them parallel to one another. Put in a switch. There's our power supply. 3 volts. Switch. The wire is our medium, and this would be our load, the bulbs. Now, in this case, if electricity travels through, as electricity goes through, all 3 LEDs will share the voltage at the same time. We don't have to worry about voltage drop. And if one of these bulbs were to go out, no problem. Electricity could still make it to the other bulbs and make it back over to complete the circuit. All right. So let's build this jammy. Let's put something together here, finally. So let's take our LEDs again and put them out in front of us. And we're going to test them. I'm just twisting up the ends here. I'm going to test the polarity to see how they're on. Okay, so that one lights up here like this. I'll put another one right on top of it. That lights up. Let's get my third one. Make it super jelly. If you don't have one of these tools, you need to go buy yourself one if you want to save time on the Amazon wish list for electricity and circuits. Great. So now I don't know which side's negative, which side's positive, but I know I have all of one polarity on one side and all the other polarity on the other, the way they're facing. You can also look at the LED, like I said, and see how the semiconductor is. There's a bigger one on the right side, and a smaller piece on the left. It'll always be the same for the polarity. You could tell that way if you wanted to save yourself time after you test them once. And you can also look, sometimes LEDs have a little mark on one side of the plastic that doesn't exist on the other side. But I just test them anyway, just to be sure. And now what I'm going to do is I'm going to take these 3 sides that are the same polarity, and I'm going to hook up all 3 of these legs together. So I'll put them together in a cluster like this and twist, twist, twist. Now I take their other leg from the other polarity, twist this up. Now I've got a cluster of LEDs that are wired in parallel to one another. Awesome. All 3 are lighting up. Super cool. So to finish off my circuit, I'm going to need to put a switch in. I can put the switch in either in between here and here, or I could put a switch in between here and here. Right? So it doesn't matter which side. I'm going to put it in over here. So I'm going to take the rest of this and tighten this all up with the red wire. And you can cover this up with one of two things. If you have electrical tape, you can take your black vinyl electrical tape, pull some of this off with your scissor, peel some of this off, cut it with your scissor. You can't, it's really hard when you go to pull this stuff, it'll just stretch on you. You want to cut it with your scissor, and you'll completely wrap up the electrical connection here so that there's no exposed wire, so that there's no chance for us to have a short circuit at any time. I'm going to use the wire caps. The blue ones are bigger than the gray ones, and if you're going to have a bunch of wires together like this, it's definitely helpful to have the blue wire cap or even an orange one. And I'm just going to fold a little bit of this over, poke myself. And I'm going to take this whole connection, this whole thing here, and put this right into the cap. You can see the cap has a little bit inside there of a threaded housing, and those threads will grab onto the soft copper. And you have to just keep twisting and pushing, and eventually they'll catch. Said eventually, there we go. Now there's no more wire exposed on that side. Get those together. And that leaves me open with the rest of this to put in a switch. So I'm going to take one of these pre-wired switches. It's already got the wire attached to it here. Right, and you're not putting the switch in on top of the lights or something like that. The switch just goes in between here and here. Right? And it doesn't matter which way you face the red or black wires on the switch. All it's doing is mechanically changing if the connection is touching or not, and so it doesn't care about polarity. So we'll strip off a little bit of the leads here. And you can use any switch you like. You can make your own switch. You could take the end of this switch and add something to it, make it bigger. The point is that you have a way to control the system, to turn something on and off. And if you want your switch to be all the way down by your feet because you've got something for collecting bugs at night, and you got to use both hands for that, and it's a lit up plastic jar, but you want to be able to turn it on and off by clicking your heels together like Dorothy, well, you're going to have to add a bunch of wire and make the switch run all the way down to your leg. Right? Then you could just extend the wire by adding more wire in any direction. You could do that for anything. Like the battery pack go feet away, make one LED come out longer than another. Just add wire on as an extension and keep going. Cross them like bunny ears and twist, 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 twist. Do the same thing over her. Oh, I know the switch is turned on because it just went on. In reality, if you're trying to get these big cluster of wires into a little end here, if you did have to feed it through a switch that didn't have leads on it like this, if you just have a switch with the prongs coming out, you'd have to feed it through that little hole. It'd be really hard to get a cluster of 3 different wire tips inside that hole. So I'd probably add a little bit of wire to this as an extension. So I had a single wire coming off and then just wrap some electrical tape around it so it wasn't exposed. And now I'm ready for a few more wire caps. And I can probably get away with a gray one this time because it's such a small connection here. I could probably even double it over on top of itself. That inside there. You see these if you take apart your wall outlet, where you put a new switch in the wall or a new outlet receptacle. You'll see this is what's connecting the wires in your house, but you know those wires are bigger. These are only 14 gauge, and the gauge of the wire gauges the gauge gets bigger in number as the gauge gets smaller as the wire gets bigger. So if this is 14 gauge, then this must be a 16 gauge because it's thicker. 14, 16, and remember when you were a kid, or maybe somebody you know now, has big gauged out earrings. I remember when I was in high school, we had 00 gauges. That was like a really big earring. Now I'll just put some electrical tape around this other connection because I don't see. I just want you to see what it looks like when it's wrapped up instead of using one of the orange ones. Get this tape apart here. And there we are. All right, so it's still one big loop, but the 3 LEDs are stacked on top of each other and wired in parallel. And we've got I know this is a latching switch because you can hear it latch and click, and it stays on. Latching and it comes off. A momentary switch or a bump switch, you just have, when you bump into it, it turns on and off. But as soon as you move away, it doesn't stay in that position. There's a spring that always pops it back. Kind of like the light that turns or the switch that turns the light on and off inside your refrigerator when the door pushes by the thing, or in the hood of your car when the hood goes up, the light goes on. So now we've got this parallel circuit, and I'll show you a couple cool things. This is a piece of acrylic. It's a piece of acrylic tubing or plexiglass tubing, and when you put light through the back of the tubing, you can see that the whole tube starts to illuminate. If I turn the lights off in my room right now, you can see the whole tube would start to glow. And the tube's really going to glow in the areas where there are scratches. Can you see how it starts to illuminate the scratches? That would tell me that clear plastic will not pick up as well on plastic that's translucent. And I could make this whole rod translucent if I were to rub sanding paper over it and scratch it all up. That would diffract the light and would pick up the light better as it moved through something like this. And this is also a little model of what fiber optic cable does. Light signals move through fiber optic cables that are a little thicker than your hair, made of glass, still operate the same way as this here. You can even see the lights probably sticking out at the end. Look at that. See up here? How cool is that? And that'll go on for miles. Now, snap circuits are a fun thing to buy if you wanted to buy circuits to play with in school or for fun at home. But you just lose the whole idea of having to think about what it is that you're doing, because in snap circuits, you just touch them together and the magnets pull them together and they work. You know, this is a lot more fun and super safe. Other than having to wear safety glasses and being worried about being poked by a wire, a short circuit, which happens if students were to, like, you know, you didn't have these connectors on, or you had tape, some of the copper was hanging out, and they ended up crossing over each other and touching inside your device, whatever you make later, you know, and that would be that's a one way they can short circuit. If you have a short circuit, if you smell something heating up, just come over here, not to the side with the spring, but the other side, push in with your thumb, and pop that battery out. Maybe you got to use your forefinger. Having baking soda, or at least warm soap, or soap and warm water. Soap would be the base to counteract battery acid. And if you had an old corroded battery that started to build up on the outside, you know, and you touch that, and you had a cut on your hand or something, you might feel it. Or maybe 10 minutes later, an hour later, that battery acid on the tip of your finger starts to work its way down. You start to feel it on the tip of your finger. That's happened to me once or twice in my life, I guess. But you take care of that with warm soapy water. All right, one last thing I'm going to leave you with the circuits that you might want to think about is, you know, this is cool, but if I want to make a parallel circuit still, but I wanted to make like a jump rope where the lights were one after another on the jump rope, and I know I have to use a AA battery pack. If I try to hook the lights up in series, one to the next to the next to the next, it definitely won't work. But if I wanted to put 20 lights on a jump rope that was 6 feet long, every one of these lights would have to be a few inches apart. And by the time I got from the battery pack out to the furthest light on the jump rope, I'd have to be pulling a wire with, like, you know, 3 feet of extension off of it. So what do you do if you wanted to make a headband where lights went around the headband, and without having to have so many extra wires, or a belt without having to take all this and add to it, so that you could put longer and longer lights on, so you could keep pulling them around to where you need them? Well, you're still making a parallel circuit, but the way that one of these would look is we have our battery pack here. All right, and here's this is not a schematic diagram. Schematic diagram actually wouldn't change. It would still be the same one for the parallel circuit. But you'd have these wires coming off your battery pack, right? And then what you would do is you would take a switch and put a little switch in here for yourself. Just draw up a switch. All right, so disconnect here and just add switch over there. One of those on-off buttons. And then we would take a piece of wire with nothing on it, just a piece of wire, right? And put a whole piece of wire down like this, connected to the end of the switch. Whole piece of wire. So now effectively, this whole run is coming off one side of the battery, plus or negative. Do the same thing down here with a second piece of wire. Connect it with a little wire cap or something, and now you have a second piece of wire run. So you could have one whole side that's basically one whole side is plus and one whole side is minus. Right now, if I were to draw this a little closer, so you can see the actual wire itself, or the coating around the wire, you could go in and take your stripping tool, or do it by another method without this tool, and strip just a little bit like that, and open up a little spot that can become a connection point along this long wire. And if I opened up a connection point in one spot, expose the wire here and directly across from it on the other wire, do the same thing here and directly across the other wire, and then do the same thing here. Put in as many as you want, like rungs on a ladder. Right? This is a ladder. You're putting in the rungs or the steps on the ladder. Each step is going to become its own LED. And I would take that LED and I would tie it in to the opening on one side and tie it into the opening on the other, and boom, it's going to light up. If it doesn't, we got to switch it over, switch the polarity. Right? So this is like a rung on a ladder, and I can put in multiple rungs, bunk, 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 all the way down. There's the light in the middle. There's the light. There's the light. And you can't connect the one end to the other at the end of it, however long this thing ends up being. You can't connect the one end to the other simply with the wire because you'd be making a short circuit. So you have to put a final LED in at the very end, right? And then tape over all your connections so there's no exposed wires. And that's how you would make a parallel circuit that continued on with a minimal amount of wire being utilized. Okay, I think that's everything I want to go over for now. Good luck. I hope this helps. Oh, yes, forgot to mention this. Alligator clips. You can get alligator clips for your kids if you were going to pre-cut wires for them and they were going to do some of this in school or anything with wires. These are called alligator clips because they're, you know what an alligator clip is, but right, there we go. You can squeeze here, open and close them. And this could be an easier way for kids to hook something right up to a wire without having to twist it, you know. Also, if you want to make any of your LEDs, illuminate better for some reason, don't just have them sticking out of a project like this. If you want to make them light up, like if you took apart a flashlight, there'd be some type of cone here around the LED that would continue to push that light out in a concave way, right? Like, this could be the LED here, pushing out the light, and you could make a little device that you could put around this thing and maybe line it with tin foil or something. And now you've got yourself a reflector, just like they put on a flashlight, right? Speaking of the flashlight, you could take that flashlight handle, if that's what you were making, and you could drill a little hole out here, pop out a hole, take your switch, if you look close, you see that it's threaded, and they give you a little nut here and a washer, and I would take the nut and the washer off, completely off, right? Then you would take the switch all by itself before it's hooked up, and you would feed it into the hole so that only the top part of the switch is out for you to see to work with, and the rest of it would be inside the device. Then you would come back up with the nut and twist it back tight, and it would sandwich itself to whatever material that is. As long as you only make the hole big enough for the switch to go into here on this part, but the hole's small enough that the top of the switch doesn't also pop through, you'll be in good shape. Chris, before you go, could you show us how to make a reflector? Sure, no problem. Let's do that. Let's take a piece of paper. So I just wanted to take a regular piece of paper and turn it into a reflector real quick. I'm on my cutting mat already. I always say I should mark what I'm making first. Cutting away from myself. Not a perfect circle. We can fix that up. Come out from the center, make a little slice. Twist it up like this into a cone. Throw a little dab of glue or some tape back there. Now I got a nice cone I could come over to the back of. Got a little bit bigger. Now my LEDs could fit through the cone. in the back. And if I line this cone with some tin foil or something reflective, this would make it so much brighter when we direct the light, right? As opposed to just having the LED sitting out there by itself. All right, great job, everybody. That's it for this lesson. And we are done.